Welcome to the quantum world. Today, we're diving into one of the most mind-blowing breakthroughs in the realm of quantum computing, Shor's algorithm. Why is this important? Because this algorithm could completely revolutionize the way we secure data. It has the potential to break widely used encryption systems like RSA, which are the backbone of online security from banking transactions to encrypted emails. But here's the twist. Shor's algorithm takes advantage of the mind-boggling properties of quantum mechanics, like superposition and entanglement, to factor large numbers exponentially faster than any classical computer could ever dream of. In today's video, we'll explore how Shor's algorithm works, why it's such a game-changer for cryptography, and what it means for the future of digital security. Stick around, because we're about to explore how the rise of quantum computers could reshape the entire landscape of cybersecurity. What is quantum computing? At its core, quantum computing is about using the principles of quantum mechanics to process information in ways that traditional computers simply can't. Instead of classical bits, which are 0 or 1, quantum computers use quantum bits, or qubits, which can exist in multiple states at once due to a phenomenon called superposition. This allows quantum computers to process huge amounts of data in parallel, making them incredibly powerful for solving complex problems. Key concepts in quantum computing. 1. Superposition. Classical bits can only be in one state at a time, 0 or 1. However, a qubit can be in a superposition of both 0 and 1 simultaneously. This means that a quantum computer can perform many calculations at once, greatly increasing its computational power. 2. Entanglement. When two qubits are entangled, their states become linked, no matter how far apart they are. Changing one qubit will immediately affect the other. This non-local connection can help solve problems much faster than classical computers by enabling qubits to work together in ways that classical bits cannot. 3. Quantum interference. Quantum computers use interference to amplify the probability of correct answers and reduce the probability of wrong ones. This allows quantum algorithms to find solutions to problems more efficiently than classical algorithms. Why is quantum computing so powerful? Quantum computers can potentially solve intractable problems that classical computers struggle with, especially in fields like 1. Optimization. Optimization problems involve finding the best solution from a set of possibilities. In industries like logistics, finance, or manufacturing, quantum computing could make decisions that are too complex for classical computers to handle in a reasonable amount of time. For example, routing delivery trucks in the most efficient way or optimizing stock portfolios. 2. Simulating complex systems. Quantum simulations could revolutionize areas like drug discovery and material science. Classical computers cannot simulate complex molecules at the quantum level effectively. However, quantum computers could simulate how molecules behave, which could lead to breakthroughs in new medicines and advanced materials like superconductors or battery technologies. 3. Cryptography. Quantum computers have the potential to break existing encryption systems by using Shor's algorithm, which can factor large numbers exponentially faster than classical computers. However, they can also create unbreakable encryption systems through techniques like quantum key distribution, QKD. This will make communication systems more secure by ensuring that any attempt to eavesdrop on a message is immediately detectable. Current state of quantum computing. While quantum computers hold immense promise, we're still in the early stages of their development. The largest challenges involve quantum decoherence. Qubits are very sensitive to their environment, and even a small disturbance can cause them to lose their quantum state, a process known as decoherence. Error correction. Quantum computers are very prone to errors due to the delicate nature of qubits. Researchers are working on quantum error correction techniques to make them more reliable. Scalability. Building large-scale quantum computers requires precise control over thousands or millions of qubits, which is a significant engineering challenge. However, major companies like IBM, Google, Microsoft, and Intel, as well as startups like Rigetti and IonQ, are all working to overcome these obstacles. In fact, Google achieved a milestone called quantum supremacy in 2019, where their quantum computers solved a problem that would have taken classical computers thousands of years to solve in just a few minutes. Real-world applications coming soon. 1. Drug and vaccine discovery. Quantum computers could revolutionize healthcare by accelerating the development of new drugs and vaccines. Quantum simulations could allow scientists to model complex molecules and their interactions at a level of detail that's impossible with classical computers. 2. Climate modeling. Quantum computing could improve the ability to model and understand climate change by simulating the behavior of molecules and chemical reactions involved in the Earth's climate system, leading to better predictions and solutions. 3. Artificial intelligence, AI. Quantum computing could help AI algorithms become much more powerful. Quantum computers can process vast datasets much faster, allowing for the development of more sophisticated machine learning models and AI systems that can learn faster and solve more complex problems. 4. Material science and renewable energy. Quantum computers could help create new materials for things like better solar panels, battery technology, and hydrogen storage, key components for a sustainable future. 5. Financial modeling. In finance, quantum algorithms could make it possible to model market behavior, optimize portfolios, and predict economic trends with much greater accuracy, helping to mitigate risks and identify profitable opportunities. Challenges to overcome. Despite the potential, quantum computing still faces significant challenges that must be overcome before it can be widely used. Some of these include building stable qubits. Creating qubits that are stable enough to perform long calculations is a huge hurdle. Cost. Quantum computers require very low temperatures, near absolute zero, to operate, which makes them very expensive to maintain. Software and algorithms. Developing software that can fully take advantage of quantum capabilities is still in its early stages. Quantum algorithms need to be developed for practical applications, like finance, medicine, or logistics. The future of quantum computing. We're in the early days, but as quantum technology advances, it will revolutionize the way we process information and solve problems. Quantum computing holds the promise of solving problems that are simply beyond the reach of current computers, and it could enable new breakthroughs in areas like artificial intelligence, drug discovery, and cryptography. So while we're not quite there yet, the future is quantum and it's extremely exciting. 1. Quantum algorithms. Quantum algorithms are what give quantum computers their potential power. They take advantage of quantum properties like superposition, entanglement, and quantum interference to solve problems much faster than classical algorithms can. Let's dive into some of the most important quantum algorithms. A. Shor's algorithm. Purpose. Shor's algorithm is used for factoring large numbers exponentially faster than any known classical algorithm. This is incredibly important for breaking common encryption methods used in public key cryptography, such as RSA encryption. How it works. Classical computers take a very long time to factor large numbers, but Shor's algorithm takes advantage of quantum parallelism, superposition, to perform many calculations simultaneously, drastically speeding up the process. Impact. If large-scale quantum computers are built, they could potentially break most current encryption systems that rely on the difficulty of factoring large numbers. B. Grover's algorithm. Purpose. Grover's algorithm provides a quadratic speedup for searching an unsorted database or solving certain types of optimization problems. How it works. In classical computing, finding a specific item in an unsorted list of items takes oxygen mononitride time, where n is the number of items. With Grover's algorithm, a quantum computer can find the item in oxygen mononitride time, which is much faster. Impact. This algorithm is useful in a variety of areas, such as searching large databases, solving optimization problems in logistics, and machine learning. C. Quantum Fourier transform, QFT. Purpose. QFT is the quantum counterpart of the classical Fourier transform, and it plays a key role in many quantum algorithms, including Shor's algorithm. How it works. It transforms a quantum state into a different basis, which can be useful for analyzing periodicity or solving problems related to number theory or signal processing. Impact. It allows quantum computers to solve problems in mathematics, cryptography, and signal analysis much more efficiently than classical computers. D. Quantum approximate optimization algorithm, QAOA. Purpose: QAOA is used for solving combinatorial optimization problems. Those problems where you need to find the best solution from a finite set of possibilities, such as route planning or portfolio optimization. How it works. It uses a quantum circuit to encode the optimization problem and a series of quantum gates to search for the optimal solution. It's particularly useful when you need to solve optimization problems that are too large or complex for classical algorithms. Impact: QAOA could help in fields like finance, logistics, machine learning, and more. Variational quantum eigensolver, VQE. Purpose: VQE is used to find the lowest energy states, ground state, of a quantum system, which is critical for problems in quantum chemistry and material science. How it works. It combines a quantum computer's ability to perform complex quantum operations with classical optimization techniques to approximate the ground state of a system. Impact: this algorithm has significant potential for drug discovery, material design, and understanding fundamental physics. 2. Building a quantum computer. Building a quantum computer is one of the most difficult and complex challenges in modern science. Unlike classical computers, quantum computers rely on quantum bits, qubits, which are fragile and need to be maintained in very specific conditions. Here's how quantum computers are built and how they work. A. Qubits, the building blocks. What are qubits? Unlike classical bits, which are either 0 or 1, qubits can exist in a superposition of both 0 and 1 at the same time. This allows them to perform multiple computations simultaneously. Types of qubits. 1. Superconducting qubits. These are tiny circuits that act as qubits and are cooled to near absolute zero. IBM and Google use this type in their quantum processors. 2. Trapped ion qubits. Ions, charged atoms, are trapped in electromagnetic fields and manipulated with lasers. IonQ and Honeywell use this method. 3. Photonic qubits. These use photons, light particles, to represent qubits, which can be manipulated using optical fibers and devices like beam splitters. This approach is used by PsiQuantum. 4. Topological qubits. This is a newer approach being explored by Microsoft that seeks to stabilize qubits by encoding information in the braid-like structure of particles. B. Quantum gates. What are quantum gates? Quantum gates are operations that manipulate the state of qubits. They are similar to classical logic gates and OR not, but they work differently because of the principles of superposition and entanglement. How it works. Quantum gates act on qubits to change their states. For example, the Hadamard gate puts a qubit into superposition, and the CNOT gate creates entanglement between qubits. Impact. Quantum gates are the building blocks of quantum algorithms. Quantum circuits, which are composed of sequences of gates, are used to implement quantum algorithms like Shor's and Grover's. Circa quantum circuits. Quantum computers process information using quantum circuits, which are composed of qubits and quantum gates. These circuits perform the algorithms by applying gates in a specific order. Just like classical circuits process binary information, quantum circuits process quantum information. The circuit depth, how many layers of gates, and quantum coherence, how long the qubits stay entangled, are crucial factors for the success of a quantum computation. 3. Programming quantum computers. Programming quantum computers is vastly different from programming classical computers, and it requires specialized programming languages and tools. Some of the key tools and languages include A. Qiskit. Qiskit is an open-source quantum computing framework developed by IBM. It allows you to program quantum computers using Python, and it provides tools for designing quantum circuits, running them on simulators or real quantum devices, and analyzing the results. It's widely used in the quantum computing community and is a great tool for learning and experimenting with quantum algorithms. B. Cirq. Cirq is a Python library for quantum circuits developed by Google. It's focused on working with quantum processors that use superconducting qubits and provides tools for designing, simulating, and executing quantum algorithms. See PyQuil. PyQuil is a library developed by Rigetti Computing that allows you to program quantum computers using the QUIL, Quantum Instruction Language Framework. It's a key tool for working with hybrid quantum classical systems. D. Microsoft Quantum Development Kit. Microsoft's Quantum Development Kit offers Q, a quantum programming language designed to make it easier to write quantum algorithms and integrate them with classical systems. The development kit includes simulators and quantum devices for testing. 4. Future of quantum programming. As quantum computers continue to evolve, so too will the tools, languages, and techniques used to program them. Quantum machine learning, QML, and quantum software frameworks will open up new frontiers for quantum computing, making it more accessible to developers and industries across the world. To sum up, quantum algorithms like Shor's and Grover's are revolutionizing computation by solving problems much faster than classical algorithms. Quantum computers are built using qubits, which can exist in superposition and be entangled, enabling massive parallelism and power. Quantum programming uses specialized languages like Qiskit and Cirq to design and run quantum algorithms. Fantastic! Let's dive deeper into quantum algorithms, specifically focusing on Shor's algorithm and how it could impact cryptography. This is one of the most fascinating and game-changing aspects of quantum computing. Shor's algorithm, a deep dive, the problem it solves. Shor's algorithm is designed to factor large integers efficiently. The ability to factor large numbers is the backbone of many widely used encryption systems, including the RSA algorithm, which secures everything from online banking to email communications. In classical computing, factoring large numbers is extremely difficult. As the size of the number increases, the time it takes for a classical computer to factor it grows exponentially. This makes RSA encryption very secure, because even with powerful classical computers, it would take years or centuries to crack the encryption key by brute force. But Shor's algorithm uses quantum parallelism to factorize large numbers in polynomial time, which is exponentially faster than any classical algorithm. This means that quantum computers could potentially break RSA encryption in a fraction of the time it would take classical computers. How does Shor's algorithm work? Let's break it down in simple terms. The algorithm can be divided into two parts: classical and quantum steps. 1. Classical step. Initial setup. First, you start with a number n, for example, a large semi-prime number that you want to factor. You choose a random integer a between 1 and n1. Then you calculate the greatest common divisor, GCD, of a and n. If the result is not 1, you've already found a factor of n, and the algorithm is complete. If not, you proceed to the quantum part. 2. Quantum step, period finding. The heart of Shor's algorithm is the quantum Fourier transform, QFT, which allows quantum computers to find the period of a function. In this case, the function is based on powers of a mod n, the remainder when a is divided by n. The period is a crucial piece of information because it can help break down n into its factors. Quantum parallelism lets quantum computers evaluate many possible values at once. This allows for the period to be found exponentially faster than classical methods. After applying the quantum steps, you have the period of the function, which is then used in a classical post-processing step to find the factors of n. Why is Shor's algorithm so powerful? Exponential speedup. The key advantage of Shor's algorithm is that it can factorize numbers in polynomial time. For large numbers, classical factoring algorithms take exponential time, meaning the time increases rapidly as the number gets larger. But Shor's algorithm scales much better. Quantum superposition. The ability of quantum computers to exist in a superposition of states allows them to perform many operations simultaneously. This leads to a massive speedup in finding the period of the function, a crucial step in factoring. Implications for cryptography. RSA encryption, which is used in secure communications and digital signatures, relies on the fact that factoring large numbers is extremely hard for classical computers. But with Shor's algorithm, a sufficiently powerful quantum computer could crack RSA encryption in a fraction of the time, compromising the security of modern communications. What does this mean for modern cryptography? If large-scale quantum computers become a reality, the widespread RSA encryption system could be broken. But this isn't the end of cryptography. The field is already preparing for the quantum threat. Post-quantum cryptography. Post-quantum cryptography refers to the development of cryptographic algorithms that are secure against attacks from quantum computers. Lattice-based cryptography. One of the leading alternatives to RSA encryption is lattice-based cryptography, which is believed to be resistant to attacks from quantum computers. These methods are based on problems like finding short vectors in high-dimensional lattices, which are hard for both classical and quantum computers to solve. Quantum key distribution, QKD. Another approach to secure communications in a quantum world is quantum key distribution. QKD uses the principles of quantum mechanics, such as entanglement and uncertainty, to create encryption keys that are theoretically unbreakable. Any attempt to eavesdrop on the communication would immediately disturb the quantum state, revealing the presence of the attacker. Challenges of Shor's algorithm in practice. While Shor's algorithm is powerful, it faces practical challenges that make it difficult to implement on current quantum computers. 1. Quantum decoherence. Qubits are extremely fragile, and their quantum states are easily disturbed by their environment. This makes it difficult to perform long calculations, especially ones as complex as factoring large numbers. 2. Error rates. Quantum computers are currently prone to errors due to qubit instability and noise. Quantum error correction techniques are being developed, but they require significant overhead, making large-scale quantum computation still very far from realization. 3. Qubit count. Shor's algorithm needs a large number of qubits to factor numbers of significant size, something current quantum computers, like IBM's or Google's, don't yet have. The quantum systems we have today are in their early stages, with a few dozen qubits at most. Large-scale quantum factoring would need thousands if not millions of qubits. Impact on security and the future. While we're not at the point of having large-scale quantum computers yet, the advent of Shor's algorithm marks a significant turning point in the evolution of cryptography and cybersecurity. Preparing for the quantum era. Governments and organizations around the world are already working on post-quantum cryptographic standards to ensure that secure communication systems will be ready when quantum computers become powerful enough to break classical encryption methods. Quantum-safe cryptography. In anticipation of quantum computers, industries are shifting towards cryptographic methods that are quantum-resistant, focusing on algorithms that will continue to provide security even in a quantum-enabled world. Where do we go from here? We're still in the early days of quantum computing, but the implications of Shor's algorithm for cybersecurity are profound. As quantum computers continue to evolve, we will see an increasing shift in cryptographic protocols to quantum-resistant alternatives. For now, quantum computers are still in the experimental phase, and it will be a few more years before we see one capable of implementing Shor's algorithm to factor large numbers. But understanding quantum algorithms like Shor's is important for preparing for the future and the potential disruption they could bring to fields like finance, data privacy, and global security. Conclusion. So what does all this mean for us? While Shor's algorithm might sound like something straight out of a sci-fi movie, its real-world implications are already being felt. We're standing on the edge of a quantum revolution that could radically alter how we secure our data and interact with technology. As we move closer to powerful quantum computers, the security of everything from bank accounts to national security systems could be at risk. But don't worry, the rise of quantum computing also brings the development of quantum-safe cryptography and new quantum encryption methods, ensuring that cybersecurity will evolve to keep pace with these advancements. As we continue to explore and understand these quantum breakthroughs, one thing is clear: the future of technology is quantum. And whether it's in the world of cryptography, AI, medicine, or material science, quantum computing is set to shape the way we live and work in ways we're just beginning to imagine. What do you think? Will quantum computers change the way we protect our data? Will Shor's algorithm truly rewrite the rules of digital security? Let me know your thoughts in the comments below, and don't forget to hit that subscribe button for more insights into the world of quantum computing.